Sometimes what's in the water is just as important as the water itself. Such is the case with our natural water systems. This chapter is all about how molecules and ions move between phases in water. We know that some dissolved ions will be in equilibrium with insoluble particles. We also know that some things may just be plain insoluble in water, but may find their way into being suspended in water anyway. We'll start here with sediments. Sediment can be formed many ways. Erosion into streams or of the lakes themselves, precipitation of dissolved ions or particles, or the joining together of dissolved molecules to form larger particles that may precipitate. A typical temperate lake bottom has layers of sediment, primarily formed from calcium carbonate and ferrous sulfide, the common name for iron 2 sulfide. The calcium carbonate is formed during the summer. The high levels of photosynthesis absorb carbon dioxide, largely as bicarbonate, and gradually raise the pH. This makes more carbonate, which precipitates dissolved calcium as calcium carbonate. And that's typically a mostly white sediment. When photosynthesis slows during the winter, the anaerobic decay of organic molecules is in part facilitated by bacteria that use sulfate, or iron 3 rather, as electron recipients for their electron transport chain in the absence of oxygen. The resulting ferrous sulfide, again iron 2 sulfide precipitate, is black and forms alternating layers with that calcium carbonate. Of course, there are other things mixed in with the sediments. The sediments contain all sorts of other particles as well. Clay particles, carbon byproducts of partial combustion, humic acids, and all of it can take other elements for the ride as well too. Gases aren't usually a separate phase in water, but do dissolve and affect other concentrations. Oxygen can get introduced by wind, wave, or current action, or to a limited extent by photosynthesis. However, photosynthesis tends to take place near the surface, and photosynthesizing organisms will eventually be eaten or decay, at which point they consume oxygen rather than creating it. Carbon dioxide and methane are also developed as dissolved gas, typically within the sediments, as that decayed matter needs to get digested anaerobically. We've already determined that Henry's law defines an equilibrium constant between atmospheric gases and those that are actually in solution. Henry's law is essentially the equilibrium constant for the reaction of dissolving something into an aqueous form. But as we saw with our in-class examples for the carbonate system, the solubility can also be affected by other ions in solution and by the pH of the solution. This is common for many gases. Ammonia, sulfur dioxide, and sulfur trioxide are all made more soluble by acid-base reactions that occur in water. Notice that the direction isn't always the same. Ammonia is basic, and so it stays in acidic solution better, whereas sulfur dioxide becomes sulfinic acid in water and stays in solution better with base. The solubility of gases also changes with temperature. The higher the temperature, the less soluble a gas typically is. But you probably already knew this. If you've ever opened a fizzy drink that was warm, you probably noticed it lost its dissolved carbon dioxide fizz much faster than a cold fizzy drink. If a colloid is mineral, it may have a coating that is either negative or positive, depending on the colloid, that tends to draw counter ion particles closer. So if we have a suspended clay particle, which is often negatively charged, it may attract positively charged ions. This matters because a clay particle can then help transport both nutrients and pollutants. Let's hone in a little more on clays. Most clays tend to be aluminosilicates. Notice that nontronite has iron instead of aluminum. Silicon normally would bond with 4 electrons, while aluminum and iron only have 3 electrons to bond with. This often means that there's an extra charge from oxygen, and that clays then become negatively charged overall. This also makes clays exceptionally good at retaining cations, including potassium, ammonium, calcium, and magnesium. The more clay content a particle or soil has, the higher we say its capacity is for cation exchange. We call this the cation exchange capacity. This can happen internally or on the surface of a material only. If it happens only on the surface, we call that process sorption. Clays serve as an important nutrient support in both water and soil. They are also incredible buffers and retain water really well. which is why my lawn seldom needs to be fertilized or watered, but it also means that it takes a lot of soil modification before I can grow acid-loving crops like blueberries. While clays are particularly good sorbents of cations and even phosphates, humic substances can also form colloids. Humic substances have charged portions and significant nonpolar regions that can sorb other organic material. Both clays and humic substances can form colloidal particles on their own, but they may also combine, and particles may have a mixture of both organic and inorganic matter, meaning that we can transport a wide range of nutrients in particles and sediments. Colloids can also entrain organic matter as micelles. A classic example is a soap. Traditional soaps are made of fatty acids, which at most pH ranges are almost all carboxylate form. The fatty acid's long nonpolar chain can interact with other organic matter, which is how they function as a soap. They can make nonpolar things more soluble in water, because the nonpolar things can interact with nonpolar, and the negatively charged head can interact with water. Similar entrainments of organic matter by natural emulsifiers can also occur, and plays a significant role in the transport of nonpolar compounds in water. In class, we talked about the specific example of an unnatural methyl tert-butyl ether as an emulsifier for the transport of benzene through groundwater. Of course, synthetic soaps can also make it into waterways. Depending on the soap and the condition, it may not be as biodegradable and can dissolve all sorts of things for quite some time. Suspended particles don't typically stay separate forever. One of two things is likely to eventually happen. One thing that can happen is that the surface charge of a particle may neutralize by an acid or base reaction. For example, a clay particle, which is typically negative, might gradually shift towards neutral. When that surface charge goes away, the particles don't repel each other anymore, and they can stick together. We call this process coagulation. If instead of using acid-base reaction to reduce a charge, we instead use a bridging compound like a multivalent cation, the particles would still precipitate, but we'd call it flocculation. The idea here is if you have a +2 or +3 charge, we can actually start to link these groups together. Both can happen naturally, but flocculation is commonly used to remove solids from water treatment. We commonly use alum, an aluminum mineral. Many trace metals can be found either sorbed to the surface of particles or in sediments. In aerobic areas of a body of water, the conditions are more oxidizing. We tend to see higher oxidation states and more oxides, hydroxides, and carbonates. In sediments, on the other hand, we have more reducing conditions, and we tend to see lower oxidation states, and in many cases, precipitation with the sulfides instead. If you've ever been to a pond, you know that the sediments at the bottom of the pond are not just solid. There's plenty of water in the middle of all that muck. We call this interstitial water. This water is in close contact with a significant amount of organic matter. And because organic matter can degrade and pull out oxygen, we'd say it's also in significant contact with a lot of biological oxygen demand. For that reason, the water will have almost no oxygen. It gets used up almost immediately. But because anaerobic bacteria will be constantly producing carbon dioxide and methane gases, it's enriched in those gases, and those gases will eventually become in equilibrium with upper waters. When they do that, they often strip out nitrogen from the water as well. We have largely been using lakes and ponds to talk about sediments in bodies of water. Because rivers tend to be moving, they often have more aerobic conditions and less sediment deposition. But when a river like, say, the Mississippi River enters a larger body of water like, say, the Gulf of Mexico, all those carried sediments are often deposited. This places all the biological oxygen demand in one place, creating lots of sediment fertility where nothing can grow because the oxygen levels are so low. It also means that rivers tend to hold on to the pollutants less, but they accumulate in slow corners and in lakes and deltas. The depth of the lake will also determine sediment patterns. As you can see in the figure toward the bottom, dominant winds can drive surface currents that require a return current below the surface. If a lake is shallow, that return current will pick up disturbed sediments. What do you think that will do for the overall oxygen levels near the surface. If a lake is deep, the return current doesn't disturb the bottom, which creates a distinctly different top layer that is oxygenated and a bottom layer that is more depleted of oxygen. A stable sediment layer is an interesting time capsule for human activity. This figure shows the depth of sediment on the vertical axis, which, because the sediment is mostly undisturbed, corresponds to the age of the sediments as well. The horizontal axis plots lead concentration. So you can quickly see the adoption and abandonment of industrial uses of lead in this record.